So now let's start talking about variable substitution in double integration and why this could be useful in many situations. Suppose you are trying to get the area of, let's say, a circle. So I have some circle, I need a solid color and no filling. So I have this circle and I want to get the area of the circle. We know that the area is equal to pi r squared, but I want to prove this result using integration. So the radius of this circle is equal to r. Now using double integration, we know that the area is equal to some double integral of dA. First, I will evaluate this integral in the regular Cartesian coordinates, so I will choose dA to be equal to dx dy. So I am choosing little rectangular sub-areas or small areas like that, and then adding all of those areas until I cover the whole area of this circle. So I am doing this integration of dx dy, and here I have my function being equal to 1. Now, what are the limits of my integration? Again, I could start with vertical strips or with horizontal strips. So suppose I start with vertical strips like that. So I will integrate in the direction of y first and then add all those areas until I finish the whole circle. Now we know that the equation of the circle is x squared plus y squared is equal to r squared. So at a certain x, we know that y will vary from this height to this height, and in general we know that y is equal to positive or negative the square root of r squared minus x squared. So at a certain x, I know that this point is equal to negative square root of r squared minus x squared, while this point is equal to positive the square root of r squared minus x squared. So I am integrating in the y direction first. So now I have this and this, then 1 dy dx, and here you know that y varies from negative square root of r squared minus x squared to the positive square root of r squared minus x squared. And after that, I will add all of those areas I got from this integration as functions of x. I will add those areas from negative r to r in the x direction. So here I'll have a negative r and an r. So this integral should give me the area of the circle. Very well. Now this is equal to, let's do the first integration. The first integration will give us a y only, and then I will substitute and finally have the integral from negative r to r of 2 multiplied by the square root of r squared minus x squared dx. Now I want to evaluate this integral. This in fact will turn out to be a slightly complex integral, and we will need to do some variable substitution in 1D. So this is not the variable substitution I am willing to talk about. I am willing to talk about another variable substitution in 2D, but that this integral will be slightly complex, and then in the next video I'll show you that a simple variable substitution in 2D will make the integral much easier to perform. So let's try to do this slightly complex integral, and let's say that we choose x to be equal to r sine u. So I am introducing another variable u. Now using this substitution, we see that the integral is equal to the integral of some other limits of 2 multiplied by the square root of r squared minus x squared. So r squared minus r squared sine squared u multiplied by dx, but dx is really equal to r. The derivative of sine is cosine, so cosine u du. So here I have r cosine u du. So this is my new integral. Now this can be simplified to be equal to the integral of 2. Here I can have r multiplied by the square root of 1 minus sine squared u multiplied here by another r cosine u du. Now what are the limits of our integral? We know that x is equal to r sine u, and so u is equal to sine minus 1 x over r. Now x varied from negative r to r, so x over r varies from negative 1 to 1. Sine minus 1 of negative 1 is really equal to negative pi over 2. Remember that the sine function can be drawn like this. So this is our sine function, something like that, then something like that. So here I have negative pi over 2. Here I have pi over 2. So sine minus 1 of negative 1 is actually negative pi over 2. So negative pi over 2 up to pi over 2. So negative pi over 2 for u up to pi over 2. So this is my integral. But remember that 1 minus sine squared u is equal to cosine squared u. So this integral is really equal to the integral from negative pi over 2 up to pi over 2 of, I can get 2r squared outside the integral. Then I have cosine u multiplied by cosine u. So I have cosine squared u du. Now how to evaluate this cosine squared u integral? We know that cosine 2u is equal to 2 cosine squared u minus 1. This is the double angle formula for the cosine. So we know that 2 cosine squared u is equal to 1 plus cosine 2u. So now this integral, I can take this 2 here and remove it from here. And let's just make this like that. So this integral is really equal to r squared integration of negative pi over 2 to pi over 2 of 1 plus cosine 2u du. Now this integral is easy to evaluate, so this will be equal to r squared. The integral of 1 is really equal to u from negative pi over 2 to pi over 2 here, then plus the integral of cosine 2u. Now this integral is equal to 1/2 multiplied by sine 2u from negative pi over 2 to pi over 2 again. So now I have this. Now the first term will give me a pi, so here I have r squared multiplied here by pi, and the second term will give me 0 because sine pi is equal to 0, so I have sine pi minus sine negative pi, which is also equal to 0, so this will give me a 0. And another way to see why this is equal to 0 is to look at this cosine 2u. So if I have u extending from negative pi over 2 to pi over 2, then 2u will extend from negative pi to pi. So I have some cosine function extending from negative pi to pi, and clearly you see that the area under this curve is equal to 0 because an area in the upside direction is a positive area while this is a negative area, so those will cancel each other. Also this area will cancel this area, and so you will get a 0 total area. So that's why this integral is equal to 0, or you can just evaluate it using this to get a 0 result. So this will be equal to pi r squared as expected. So that was a slightly tedious integral. In the next video, I will perform one simple variable substitution to my very small area, and this will make the integral much easier to evaluate.